Going into topic 3 now of Unit 2, we're going to deal with exponential and logarithmic functions, applications, and models. So no notes yet. This is just the topics that we'll be covering. And here we start. So what is an exponential function? Well, let's analyze it. You'll be writing this in your notes. We have the symbol for function, f of x. Now, b is for the base that's raised to some exponent. So this is the official formula, sounds like a good quiz question, of exponential function. Now, the base has to be greater than 0, and the base cannot be equal to 1. So these are some qualifiers of the value of b. Now, what I'd like to do here is have you put this in your notes. So on this side you will sketch a graph here, and then you want to make two t-charts. And we're dealing with exponential function. That is, the x is the variable as the exponent. And we're going to physically do some t-charts so you can get some background on how this is done. So we're going to have y equals 2 to the x power, and then in blue we'll have y equals 1/2 to the x power. And we want to see what kind of graph is going to be made when we do this. Alright, so let's start filling in. If you've copied this down, you'd have to pause it. So we have 2 to the 0 power. X is going to be 0. Well, anything to the 0 power is 1. 2 to the first power is 2. 2 to the second power is 4. 2 to the third power is 8. Now you may or may not know what 2 to the negative 1 power is. So let me just do that for you. This is equal to 1 over, you take the exponent and the base to the denominator, where the exponent then becomes positive. So this would be 2 to the first. So in a sense, when you have a whole number to a negative exponent, it just becomes the reciprocal of it. So what is the reciprocal of 2? 1/2. Okay, now let's do the next one. 2 to the negative 2 will become 1 over 2 to the second. Bringing it down to the denominator changes the sign of the exponent. And what is 2 to the second? It is 4. Okay, 1/4. So 2 to the second is 4. The reciprocal of 4 would be 1/4. So these are just the reciprocal of what we have up here. So to the first is 2, so this would be 1/2. This is negative 2, so that would be 4. The reciprocal is 1/4. And this one is 1/8. Now, we'll do this one here too, and we're going to change colors. Again, 1/2 to the 0 power. Anything to the 0 power is 1. Now, 2 to the 1/2 power, 1/2 to the first power is just 1/2. 1/2 to the second power is 1/4. 1/2 to the third power is 1/8. Now, the negative will be the reciprocal. So the reciprocal of 1/2 is 2. The reciprocal of a 4, 1/4 is 4, and then this one is 8. So there is a little pattern and a lot of math. And again, you don't need to know all of this, but you want to now be able to plot this on this graph. So we're going to go to red now as we plot these. X is 0, y is 1. So x is 0, y is 1. We get a dot right there. 1 and a 2. So over 1 up 2. We get a dot right there. Over 2 up 4. We get a dot right there. Over 3 up 8. We get a dot right there. Now 1/2 is there. 1/4 is there. 1/8 is there. Would be 1/16, 1/32. We're just getting some points so that now we can sketch this curve here, if I can do it very carefully here. Let's get a nice curve in there. And this is the typical curve of the exponential function 2 to the x power. Now, on your test, and often in your homework, you're going to have multiple choice, and you're going to pick out, anytime you see an equation like this, a function base to an x power, if it's a whole number, it's going to look like this. Now, it's going to go sometimes a little closer, maybe a little bit further out this way, but this will be the general pattern, and that's what you need to know. And you're going to have that in your notes. Now I'm going to change to blue, and we'll plot the 1/2 power. So 0 to the x to the 0 is going to be 1 still, right there. And then we go, if it's, let's do the negative ones first. -1, it's 2. So -1, it's 2. -2, it's 4. -3 is 8. And let me sketch these in here if I can here. No, I'm not doing that too well. Try again. In fact, let me pause to do it. Now, in the fraction form, you're seeing what's happening here. The curve is starting high, going down through 1, and then off in this direction. So as we look at this, I don't know if you can notice, but the red line and the blue line, if we folded the graph over our x-axis, this is a mirror image of the other. And this y-axis is called the axis, put this down here, of symmetry. The axis of symmetry, because what's on this side is the mirror image of what's on that side. Ah, now, my point to you is that if you ever see they want you to graph a function in which it's a fraction raised to the x power, and we've done the data, we've plotted the points, it's going to start high and it goes down. Now I'm showing you this so you'll have this in your notes and have a good background for it. Okay, we're going to move on now. So we've done that. Now we have to add one term, and I wanted to have this nice slide to do it. As this line, this blue line here, gets closer and closer to the x-axis here, it never reaches the x-axis. It keeps getting smaller and smaller and smaller and smaller, smaller and smaller fractions, but never reaches the x-axis. When we have a condition like this, when a line approaches something but never quite reaches it, we call that an asymptote. And since the asymptote, which is the x-axis, lies horizontal, we call the x-axis, sounds like a good quiz question for me, the horizontal asymptote. What is an asymptote? It's a line that something gets close to but never reaches. Now, one of the questions they will ask us here, and I want to include that, is what would be the domain and what would be the range of this? Well, this is going to go off to negative infinity for our x values, and then eventually go off in this direction to positive infinity. So the domain of this graph, and of the fraction one too, the 1/2 to the x, is going to be the same, but it will come down this way and go this way. Now, the range, though, remember, what value is the y here? Well, if the axis itself is 0, but we're saying this line never reaches 0, so we use a parenthesis for 0, and then it's going to go up to positive infinity in this direction. Okay, some more items, and you can add that to your previous work here. The horizontal asymptote. And there is your fraction raised to the 1/2 power. It still has the same horizontal asymptote. The range and domain are the same. And here they're just summarizing what we've just done here and giving you the domain. The domain, all real numbers. The range, starting at 0, not reaching 0, because that's an asymptote, but going to positive infinity for the y values. Now, we had mentioned Euler's E, which has this value, and what would that graph look like? Well, very similar, except instead of being here, and I'll write it out for you, instead of this being a 2 to the x power, it's going to be 2.718 that we rounded it off to. So again, if this were 0, this to the 0 power is 1, but then instead of going through 2, it goes up here, where it's about 2.7. So a very similar curve for base E. Now, we're moving into the use of these exponential functions, and we're introducing other formula. So, right now, you're going to write what is called the compound interest formula. Now, what is it? Well, we have an A, which is referring, and I'll switch to red here because that makes it stand out. The A stands for the future amount that you will have. P is the amount of principal, and you'll see some examples very shortly. And then in a big parenthesis, we have a 1 plus a rate. Now the rate is usually given as, let's say, 5%, but in this formula you have to convert that to its decimal form, which would be 0.05. The n refers to the number of times that during a year the interest is compounded. So this is the number of times it's compounded during the year. And then up here in this position we have n, which is that same value n, that's multiplied by t, which is the number of years. Okay, so they describe it here too. This is the official formula for compound interest. Let's go on. Now, this is example 3. Hopefully you've listed your other examples earlier that we've included in that original item. Let's fill this in and see what we get. So A, we don't know A. That's going to be the future amount. Now our principal is $2,000. A big parenthesis, a 1, plus, what will our rate be? Well, it's going to be 8%. So we convert that to its decimal fraction. And it's going to be compounded quarterly. Now in a year, quarterly means 4 times. And this is going to be for 6 years. So it'll be 4 for the n, which is the quarterly period here, and then 6 years. So this number, we can do this. This is 4 times 6 is going to be 24. So I can just put the 24 there. So you see where it came from. Now, the key to this is being able to put this into your calculator and get a good answer. So I suggest you would start with, in your calculator, turn it on, do 0.08 divided by 4, and then add 1 to it. That'll give you what's in the parenthesis. Then you're going to use the caret symbol to put in your exponent, which is 24. Hit enter. It'll give you a value. Then you multiply it by 2,000. And then it'll give you an answer. Now you should be trying this out to be sure you know how to use your calculator and get the answer we're going to show you in just a moment. So there's the setup, and then there's the future value. They usually want you to round it off to the nearest whole cent. So are you getting this in your calculator? That's the key. So pause and check your work, because you'll be getting examples like this in your homework. Okay, now we have another formula for what is called compounded interest, but it's continuous. So this is a little different. Now, in the previous example, we were compounding, in this case, 4 times, quarterly. But how about if you compound continuously? That is, moment after moment, you're compounding. Well, here is where Euler's number comes into play. So the formula for this would be A, your future amount, is equal to the principal times E, but now E is raised to the rate times the year. Alright, so again, your exponent is going to be a little bit tricky here, but there's your formula. future amount times the principal times E. So you'll have to find where E is on your calculator. And then it's raised with a caret. You put this usually in a parenthesis. Rate times the number of years. Okay, let's look at an example of this. We went back. There we go. So let's set this one up here. So future amount equals the principal, which is $2,000. Now we're going to multiply it by E, and the interest rate is 8%. So I'm going to put this in a parenthesis here. And we're going to times this by 6 years. Now you might say, how would I do that? Well, theoretically, you could put the 2,000 in, you get the E coming up, put your caret in, put this in parentheses, it's all one example, and then hit enter, and that's going to give you the answer. Now another way to do it is to put the E in, raise it to this power, put that in parentheses, then multiply it by 2,000. And again, you're trying this out to see if your calculator is working and doing what it's supposed to be doing. And there we have it. And then there's the answer. Now you'll notice this is a little bit more than we had in the previous slide. Why? Because you're compounding it continuously. Okay. Now, we can modify our exponential formula by doing what we call a growth function. And this is the official formula for it. A of t, this is a function, is your initial value of a, that a sub 0 is what it was originally, times e, and then your k is going to be some value, in this case, greater than 0, and then your time is going to be whatever number of years you have. Now, if the k is greater than 0, you have what is called exponential, let me highlight this for you so you see it, exponential growth. But if k is less than 0, you're going to have what is called exponential decay. So let me just graph that a little bit for you. And we're dealing with the first quadrant. Exponential growth, remember, looks like so. Exponential decay may look like this. So increasing is growth, decreasing is decay. Just to give you some background on this. All right, let's go on to see what they're going to give us here. All right, we're going to get to some of this a little later, and you'll be using some of these formulas, of course, for your homework, and that'll give you the practice. Now, we'll also do some examples, probably on a second part 2, because there's lots of stuff here in this lesson. Now, what we're going to do is give you a definition as background of what logarithms are. And for this slide, we'd like you to include this little diagram that I'll pause, sketch, and then you can put it. So in your notes, next little area, you're going to put the definition of log, base b of x. That is, what is the relationship between, and I'll change colors here a little bit here, what we've just had. This is the exponential form. What we've just done. So we've said 2, for instance, to the third power, which is 2 is the base, 3 is the exponent, equals the answer of 8. Now, when we write in log form, this is the log form, logs basically are just exponents. We're going to say log, and let's write this word down, log. And we're saying of a base. So our base here is 2. So we're going to say log of base 2. And we're saying the answer goes here. Well, the answer we said was 8 equals the exponent. And the exponent is 3. So this is the exponential form. This is the logarithmic form. And this is sort of the recipe for converting one to the other. You're just rearranging things a little bit. So your base, here it's 2 an exponent, gives you the answer. Here it's the base of the answer, gives you the exponent. Now, this is all set up in your calculator. In the old days, people had to look up charts to see what the exponents were, the log for of these values were, and they had to calculate them all by hand. It was quite a job. Okay, so hopefully now you have this in your lesson, and then here this is going to be equals y here. They didn't quite finish that. So log of the base, the answer is x, equals the y that comes over. Okay, lots of stuff here. And again, that you can use your notes. That makes it very nice. Now, here, I would write these into your notes. And let's just work them. Now, one of the things they've done here is they have put the equal sign on this side. I'd rather have the equal sign on that side. And then equals 4, I should say. We'll just take these away here. Because that's the way we set it up in our other chart. Alright, so let's just do that now. So 3 is our base to the 4th power. Exponent is the answer of 81. So putting it in its logarithmic form, the log of our base, which is 3, our answer is 81 equals the exponent 4. Now this is 10 is our base to the 4th power equals 10,000. So our base, log of our base 10, the answer is 10,000 equals the exponent 4. Now, this one's a little tricky because it's a negative exponent. That's fine. Remember, this answer, let me write it a little better here. 4 to the negative 3 is actually 1 over 4 to the 3rd, which is 1 over 64. I just have this written funny. So anytime you see a value base to a negative exponent, it's going to be some sort of fraction. So once again, log of our base, 4, the answer is 1 over 64. That's going to equal the exponent, negative 3. And this one's a little tricky too. You'll see this. So our base is 3. Our answer is 1. And remember, any base to the 0 power is 1. So if our answer is 1, our exponent is going to be 0. Okay, so as you copy it this way and make these fractions look proper. I don't like the way they write it here. They could have written it the proper way, but I guess for expedience they wrote it this way. Alright, let's go on. Because we're going to be using logarithms for our calculations. And there's the basic function that we've already described. Now, how about the graph of our logarithmic functions? Now, I could set it up like we did, but all I'm going to ask you is to remember what the overall shape of the graph looks like. Now, we're going to introduce what is called the vertical asymptote in just a moment. Right now. Okay. Now, what I'm going to put on here is what we had before, and just sketch it in so you have a rough idea of it. I'm going to make a little finer point here too. So if we had f of x 2 to the x power, our graph looked like this. Now, if this is the exponential form, the logarithmic form of that same graph is the mirror image but goes in this shape. So you're going to sketch this down. You don't have to put this red line in because that was for this. And it's the reflection. Now, interestingly, it's a reflection along another axis. This line that goes through the origin and cuts it right down the middle. If you folded this along this line, which again is referred to as here the axis of symmetry, and the equation of that is y equals x. For any of you who want to know that, but just remember there is an axis of symmetry there, and for a log of 2 and a power base of 2 here, in its exponential form the graph would be like so, but in its logarithmic form the graph is like so. Now notice that this line here gets closer and closer now to the y-axis. We call the y-axis here, as we mentioned before, the vertical axis, and that would be the asymptote. The vertical asymptote is the y-axis. So lots of detail of math background. Again, having it in your notes, having good notes that you can use for our quizzes and of course for your test. Now, when we do the fractional form of this, where the whole number base went this way, the fractional form goes this way. And if you recall, the fractional form of our whole number went this way here. But all you have to remember, I'm going to take this off here so it doesn't confuse here, is if the log is in its fractional form, the graph of it goes like this. So generally all they want you to do is pick out from multiple choice which graph is applicable. Now, let's look at the domain and the range in its logarithmic form. Now, as you probably imagine, this goes down for range to negative infinity, and eventually we'll go up here to positive infinity. But how about the domain? Well, we say it gets closer to 0, which is our x value here, but never reaches it because of the asymptote. Well, our domain then would be a parenthesis for 0. It never reaches 0 here, but goes to positive infinity. So in its logarithmic form, I don't know if you've noticed this is just the reverse of what we've done for its exponential form, for its domain and range. And again, this is example 5 pp. And here is the summary in words of what we just showed you in the diagrams. So going back, again, if it's a whole number log, the graph will look like this. If it's a fractional log, it'll look like this. That's what you need to remember. And we did go over the domain and range. And we defined the vertical asymptote as the y-axis. Okay, now if we had the log, which we call the natural log of e, the curve is going to be similar. But instead of going through 2, it goes a little higher here at about 2.718. Okay? And the shortcut way of writing it here is ln. This is not a 1. This is an L. This is for natural log. Natural logs involve the letter E. And again, just a sketch of this would be fine. Now, this is something that's going to be very, very useful. And we're not going to mention it a lot, but when we do calculations using logs, natural logs, this comes into effect. And let me write this down. This is going to be significant here. So here's the basic thing you're going to write. The natural log of e to the k power. Now, what is the base of natural logs? Well, the base of natural log is e that they don't write here. So these two e's, and there's a kind of a calculation that goes on, that whenever you see this exponent up here, that becomes your answer. So this configuration is going to equal k. And I'll show you this in a little while. Alright, this is example 6, doubling time. Suppose that a certain amount P, which is your principal, is invested at an annual rate of 5%, compounded continuously. How long will it take for the amount to double. That is the doubling time. So that's the background. And here is our equation. And I'll work it out for you as well. So our amount equals our principal, ERT. This is one that we had for continuous interest. Now, do we know how much the future amount is? No. Do we know how much P is? No. But we know we want this P to double. So we can replace the A here with 2P. That is, 2 times P would be the doubling of P. All right. Now we're going to use a little bit of algebra. We're going to divide out our P's. So the P's cancel out. So what are we left with? This right here. Okay? So again, you're just writing these down in a sequential pattern, and we're showing you the algebra to get there. Now, this is what we have from the previous slide. And we're going to do some fancy math. Again, beyond what we would normally do in a course like this, but we need to use now logarithms to solve when we're trying to find out what an exponent is up here, our t. And what we do is we convert this in its exponential form to a sense in its logarithmic form. And since it's e, we're going to use the natural log. So natural log of 2 and the natural log of e to this power. Now, I don't know if you remember from a previous slide just a few moments ago, we said when it's in this configuration, it is just the exponent that comes out on this side. This equals that. So that's where they got this here. So they went from this, remember there was an e here, this became just the exponent. So now, with that mathematical magic, we can solve for the letter t. You might say, how would you do that? Well, you're going to divide now both sides by 0.05. That'll give you the t that they're putting over on this side. And you're going to divide the natural log of 2 by 0.05. Now, this is what you put in your calculator. The natural log, and you have to try this, the natural log of 2 divided by 0.05 gives you this. So the answer statement is going to be, it's going to take about 13.9 years for that principle to double in its value. Wow. The use of mathematics. Now that was an increase exponentially. We're now going to take a look at a model in nature. And for any of you that have biology background, this may be familiar. I have a biology background, so I'm familiar with this myself. Radioactive material disintegrates according to an exponential decay function. The half-life of the quantity that decays exponentially is the amount of time it takes for any initial material to decay to half of its initial value. And some background on this is while a leaf or piece of wood is alive, the amount of radioactive carbon-14 is sort of in equilibrium with it. The amount going in is about the same. Now, once it dies, it doesn't take any more radioactive carbon into its system. So, from the point of its death, as it, over the years, if it gets preserved somehow, the item, the skeleton, the piece of wood, we can test it in the lab to see how much carbon remains, carbon-14 remains. And then we can figure out its age through this type of mathematical analysis. And there is the formula. Y equals the initial amount of carbon-14 using E. But notice now our exponent is negative, and we want to solve for T. Alright, so this is example 7 for our PowerPoint slides. So what, first of all, is the half-life of carbon? Now, if the initial sample contains 1 gram of carbon-14, how much will be left in 10,000 years? This is a dating tool that biologists can use. And let's see if we can follow this through here. And I'll move this down so we can go through the whole thing. So, there's our initial formula. You're going to copy that down. That's straightforward. Now, we're going to say we want to find, now we have half of it left. So what we're going to do here, and it's a little tricky, so let me write it out for you. There's our initial amount, right? So we're going to convert this to its natural log form. Natural log of 1/2. And then this then, when we convert this side to natural log, they're not showing us this. This then just becomes the exponent. That methodology. So what we do is, remember we can put 0.5 here in our calculator when we're figuring this out. We're going to divide both sides now by a negative 0.123, 3 zeros, 1, 2, 1, 6. And then this side by the same thing. Put that in your calculator. You should try this. All of this cancels out on this side, so we're left with T. And when we do it, we find that half-life is about, and this is real, it's not a made-up thing, 5,700 years. So we're figuring here that if you had 1 gram to start with, if when you tested your old relic or whatever, how old was it? When did it die? It has half of what was there, and we get the answer of 5,700 years ago. All right. Now, continuing with the answer, we know we have 1 gram, but now we know we have 10,000 years, so we put T as 10,000. We started off with 1 gram. E, we know, put that in our calculator, just put E, and then a caret, and then put all of this in parentheses, and it comes out to be about 0.3, which is about 30 or 3/10 of a gram remaining after 10,000 years. So that's the second part of that problem. Okay, we're going to make this into 2 lessons, or 2 parts. This one is long enough for our basic material on exponential and logarithmic mathematical background items.